Okay, I'm going over the SN1 mechanism, which stands for Nucleophilic Substitution 1. It's very different from the SN2 mechanism. The primary difference is that you get this formation of a carbocation. And unlike the SN2, in the SN1, you get kind of a racemic mixture of stereoisomers at the end. And it's kind of a consequence of the carbocation formation. So let's real quick go through the mechanism. I'm just drawing the overall reaction here as you can see it. The overall reaction is identical between the two different SN1 and SN2 mechanisms, but as we go over the SN1 mechanism, you'll see it's pretty different. Okay, so let me get started here. And you'll also notice I'm drawing a tertiary carbon here. With the SN1 mechanism, the more highly substituted a carbon is, the more reactive it is. And that's the exact opposite of SN2 mechanism. So what we have going on here is the bromine leaves with its pair of electrons, and then you get this formation of a carbocation, which is a pretty unstable intermediate, which consists of a carbon that has a positive charge on it. And then the bromine is leaving with that electron pair. Okay, next we have water coming in, and it's going to act as the nucleophile. Water is not a great nucleophile. That's another kind of interesting part of the SN1 mechanism. You don't need a really strong nucleophile for it to work, because it's primarily the leaving group. If it was a strong nucleophile, you could have kind of an SN2 mechanism where the attack comes in and knocks off the leaving group. Anyway, so let's go here. We have OH donates its electron pairs to that unstable carbocation center, and so then you get this kind of intermediate formed where water is not a great nucleophile again, is attached to that carbon center. So then we have, the carbocation gone. Then we're going to get this proton is going to leaving us with an alcohol. Yeah, and there's our alcohol. And we have the bromine from earlier, so you get HBr. Just some quick notes on this mechanism. This one's pretty important. You form a racemic mixture of products, and here I'm going to go ahead and draw out that key carbocation step, just so you can see how we get a mixture of the two different stereoisomers. Now here I'm putting R1, R2, and R3, not like in the previous mechanism where they were all methyl groups. Obviously, if you have like 3 methyl groups there, then both of the enantiomers are exactly the same molecule. But if all these groups are different, then you get 2 different products, which kind of differ only in the stereochemistry. So anyway, let's continue. Here we have formation of the carbocation again. And you see, when that carbocation leaves, when the bromine leaves, you had a tetrahedral molecule, but as that bromine leaves, you only have 3 substituents on that carbon, so you go to a trigonal planar. It's kind of a flat thing with kind of 3 substituents on it, and it's flat, so there's kind of, you can attack from the top or the bottom. And the way I've drawn this, I'm kind of trying to draw R2 in the back and R3 kind of coming toward us. I hope that's clear. Anyway, that trigonal planar carbocation, and here's water again, and water can attack from both sides. Let's just draw both of those little attacks out. So here's what happens when it attacks kind of from the right side as I have it drawn. You get the water there, and that's 1 stereoisomer. And if you do your Kane-Ingold pre-log rules, depending on what those substituents are, it would be R or S, depending on what R1, R2, and R3 are. The R enantiomer or the S enantiomer. So that's 1, and there's the proton leaving, so you get the alcohol. And let's do the other one real fast. I've drawn it in red there, just so you can see. It attacks from the other side, like the left side. Like imagine it as a flat trigonal planar molecule, and you can get kind of an attack from the left or right. on this one, I'm attacking from the left, and these molecules look the same, but this is actually different. With the oxygen on the left here, if R1, R2, and R3 are different, these two molecules are now non-superimposable mirror images. And that's the definition of an enantiomer. So they're actually different molecules, and this is pretty important. And since you get this carbocation formation, you can have attack from either of these positions, so you form both of these products. So if it's possible, if your thing goes by this mechanism, you should get a mixture of products.